So once we know how to do long division with polynomials, or more specifically the synthetic division like we just practiced, a couple of theorems emerge. One of those is called the Remainder Theorem, and another one is called the Factor Theorem. These are some natural kind of consequences, if you will, from long division. Now, that word theorem means it's not only a theory that someone just thinks, but it means that it can be proven using a mathematical proof process. I'm not going to ask you to prove it, okay? There are proofs in your book if you want to look at those, but I'm not going to ask you to prove it, but I am going to ask you to be able to use it. Okay, so let me show you what this remainder theorem is actually saying. It is saying that if you take polynomial f of x and you divide it by x minus c, now c could be any number. So you could divide by x minus 3, you could divide by x minus 8, you could divide even by x plus 2, because putting a plus right here would mean that you minus a negative, okay? Then the answer you get to that division, that remainder, okay, the remainder that's left over when you do that division, will be just whatever f of c was. All right, so in other words, if you wanted to find, let's say, f of 4. F of 4 means you take the function f of x, and, let's say f of x was 3x plus 2 or whatever, and you put 4 in for x. Well, f of 4, let's see, 3 times 4 is 12, plus 2 is 14. What that is saying is that if you took this 3x plus 2 and you divided it by x minus 4, then I would get the same thing as if I just put 4 in that polynomial. Let me prove to you that that's true. If I wanted to divide by x minus 4, I'd put a positive 4 in the box, and my coefficients here would be 3 and 2. Bring down the 3. 4 times 3 is 12. Combine those, we get 14. Our remainder is 14. So notice what just happened. Plugging in 4 for x in the original polynomial gave me 14. But dividing 3x plus 2 by x minus 4 gave me a remainder of 14. That is a verification. Well, that's one example, not really proof for a verification, but it's one example that if you divide by x minus a number, that's the same thing as just plugging in whatever that original number was into the original polynomial. Okay? That's called the remainder theorem. Let's do a couple others to verify that. Okay? All right. So here's a polynomial f of x. They want us to use the remainder theorem to evaluate f of negative 1. The remainder theorem says that instead of evaluating that f of negative 1, we can pretend that we're going to divide by x plus 1. Okay? If I'm dividing by x plus 1, that's putting negative 1 in the box and writing out my coefficients. So I've got the 5 for x to the 7th, a 0 for x to the 6th, a negative 3 for the x to the 5th, a 0 for x to the 4th, a 0 for x to the 3rd, the 2 for the x squared, a 0 for the plane x, and then our negative 1. I'm going to do my synthetic division. Remember, every time I bring a number below the line, I multiply by the box. Okay, I did that really quick. Hopefully you're getting better at synthetic division. You can do it quickly as well. Okay, the remainder is the number I'm interested in. Okay, so when I did synthetic division, I found the remainder to be negative 1. That means that if I just plug in negative 1 for x in the original polynomial, 5 times negative 1 to the 7th minus 3 times negative 1 to the 5th plus 2 times negative 1 squared minus 1. If I work this out, I ought to get a negative 1. Let's see if that happens. 5 times negative 1 to the 7th minus 3 times negative 1 to the 5th plus 2 times negative 1 to the 2nd minus 1. Sure enough, that works out to be negative 1. So plugging in negative 1 is the same thing as if I had divided by x plus 1. Remember, dividing by x plus 1 means you put a negative 1 in the box. That remainder is the same. Okay? Now, I don't love that we plugged in a -1 and our answer came out to be -1, so let's try another number where they don't come out the same, okay? Given that f of x is this guy right here, find f of 5. Now, obviously, f of 5 means put 5 in for x and work this out. But a shortcut would be to say, hey, if we're finding f of 5, 2 times 5 to the third minus 7 times 5 squared minus 5 times 5 plus 4. I can work that out with my calculator. And I get 54. Okay? But that's the same thing as doing synthetic division. Coefficient of 2, -7, -5, and 4. And I'll be honest with you, I think I could do that synthetic division faster than I was able to plug 5 in, even with my calculator. But notice they both came out to be 54. So what we've discovered is that f of 5 is 54. And I could have just plugged in 5 for x, but the remainder theorem says, you know what, you could do synthetic division. And whatever the remainder is what you would get if you put in that 5 for x. I personally think on this one, I can do it faster with synthetic than I could have even typed this in my calculator. But definitely, if you didn't have a calculator, synthetic would have been a lot faster. Okay? All right, that's the remainder theorem. The factor theorem says that if f of c equals 0, then x minus c is a factor of f of x. Now let's think about that, what f of c equals 0 means. In other words, a while ago we found f of 5 was 54. We found f of -1 was -1. Neither of these two examples we just did came out to be 0. But if they had, that would mean that we had found a factor. So, back over here on this number 3 from the earlier video. Well, that one wasn't a pretty one, but the remainder was 0. That meant that whatever we divided by, the 2x plus 8 or the x squared minus 3x plus 4, those were factors. Okay? Where was another one that was a little bit nicer? Here we go. Number 7. When we divided by x plus 10, notice when we divided by x plus 10, we put a -10 in the box. Our remainder was 0. That means that the original x plus 10 was a factor. Because if the remainder is 0, that means nothing was left over. It divided evenly. Okay? That's exactly what this is saying. If your remainder is 0, then you found a factor. Okay? So use the factor theorem to determine if x plus 4 is a factor of this guy. Okay? Well, if x plus 4 is a factor, then when we divide, the remainder should be 0. Okay, so let's write out our coefficients. 6, 11, -60, and -32. We're dividing by x plus 4, then -4 is what goes in the box. Write down my first coefficient and multiply by the box. Combine, and we get, what is that, -13? Multiply, combine, multiply, combine. And sure enough, our remainder is 0. So, yes, x plus 4 is a factor of f of x. And we know that because the remainder is 0. Okay. Now, one other thing I want to point out about this. Since x plus 4 is a factor, we say that -4 is a 0. Some people call that a root. All right, let me show you what I mean by that. Let me go into my calculator here and graph this. I graph 6x to the third plus 11x squared minus 60x minus 32. I'm typing that equation in and I'm going to graph it. Notice that this function hits the x-axis at -4. Remember in 3.2 when we figured out how to find the zeros and we would write this in factored form? If x plus 4 is a factor, then -4 is a zero. -4 is a place where this graph hits the x-axis. Okay? In fact, this original polynomial would factor to x plus 4 times 6x squared minus 13x minus 8. Okay? And then I bet this one would factor again, okay, into two more pieces. And we'll look at that a little bit later, how that works. Okay? But just know that if you find a factor, then whatever you put in the box here is a zero. That is a place where the graph will hit the x-axis. I usually call them zeros. Some books call them roots. Okay? All right. Use the factor theorem to determine if x plus 2 is a factor of this polynomial. Well, if x plus 2 is a factor, then that means f of -2 would need to equal 0. So I'm going to put -2 in my box, and I'm going to write my coefficients out here. 1 for the x to the 4th, -1 for the x to the 3rd, -11 for the x squared, +11 for the plain x, and 12 for my constant. I'm going to do synthetic division, and I'm going to see if I get a remainder of 0. I bring down my first coefficient. Anytime I bring something down, I multiply by the box. And then I combine. Multiply by the box, combine. Times the box, combine. Times the box, combine. Let's see, 12 minus 42 is what, -30? Okay, I did not get a remainder of 0. Since I did not get a remainder of 0, then I'm going to say no. X plus 2 is not a factor of f of x. And the reason I know that is because the remainder is not 0. If I graph this thing in my calculator, it will not touch the x-axis at -2. Okay? X plus 2 is not a factor. I want to graph that. It is a polynomial function. It does hit the x-axis in a few places, but -2 is not one of the places it touches. And it does not touch at -2 because x plus 2 is not a factor. How do I know that x plus 2 is not a factor? Because when I did synthetic division, my remainder was not 0. Okay, let's look at number 12. Notice they want us to see, or to show, that square root of 5 is a 0 of this thing. Well, if square root of 5 is a 0 of this, then that means x minus the square root of 5 is a 0. I'm sorry, is a factor. Okay, well, if x minus square root of 5 is a factor, then positive square root of 5 is what would go in the box. And I'm going to write out my coefficients. 1 for the x to the 3rd, -4 for x squared, -5 for the plain x, and the 20. And I better get 0 as my remainder if, in fact, square root of 5 is a 0. Now, this is a little weird because of the square root, but we can still do it. Bring down the 1. 1 times square root of 5 is square root of 5. Then we combine these. These are not like terms. -4 is a whole number. Root 5 is a radical number. Okay, they're not like terms. But I can keep that as -4 plus root 5. They're not like terms, but I can still write the whole thing down. And now root 5 has to multiply by this. Well, root 5 times -4 is -4 root 5. Root 5 times root 5 is square root of 25, which is just plain old 5. Combine my like terms. -5 and +5 cancel and leave -4 root 5. And then when I multiply root 5 times negative 4 root 5, I get negative 4 root 25. Well, root 25 is 5 times the negative 4 that's already there, and I get negative 20, which does leave a remainder of 0. If that is challenging, because doing synthetic division with radicals is definitely something that could be challenging. So notice that I could also have considered it to be, hey, why don't I find f of root 5? In other words, put root 5 in for x. Root 5 to the third minus 4 times root 5 squared minus 5 times root 5 plus 20. Since my remainder here was a 0, then this better work out to 0. And this I can use my calculator for. So this is kind of cool. Square root 5 to the third minus 4 times square root of 5 squared minus 5 times square root 5 plus 20. And that also works out to be 0. So I could have done it either way. Remember, to find out if something is a 0 or not, you need to see if the synthetic if division gives you a remainder of 0, or if just plugging that number in for x gives you a 0. So yes, we've shown we know x minus root 5 is a factor, and square root of 5 is a 0 because the remainder is 0. Okay.